Now I would like to invite the first lecturer, Kavli Prize Laureate in Nanoscience area, Professor Thomas Epson. Please watch the video of Professor Epson that was shown at the time of the prize presentation ceremony.
Their beauty, and science is a way to satisfy my curiosity. The discovery for which I'm recognized was quite an accident. I wanted to control the properties of molecules by putting them in tiny metallic test tubes. So I asked a colleague if he could make me such a small structure. So a couple of months later he comes back with a gold film in which there's a square centimeter of 100 million holes. To my surprise, I can see through the holes, just like tinted glasses. And if you know some physics, you know that this is highly unlikely that light would get through these holes. And I spent the next 7-8 years trying to understand the phenomena before I finally published it.
Professor Epson's achievement is about light that goes through tiny holes, as the title says. Let's say we have a screen and there is an Indian elephant that went through the hole. It was as surprising a find as that was. And you might think that that is not possible. And Professor Epson repeated experiments to see whether this is for real or if it was a mistake or artifacts. And after many repeated experiments, he was able to convince himself that this was real, but it could not be explained. So for 9 years, he could not publish. But at long last, his paper was published. And for that, he was recognized with Kavli Prize. And he is also a Japanophile. And he was at NEC Research Institute, and he conducted the research there for 9 years when he discovered this phenomena. And his wife is Ms. Masako Hayashi. Her maiden name is Hayashi, and she's a pianist. Professor Epson is a very fun person, so I'm sure the audience will enjoy his lecture.
Konnichiwa.
Good afternoon. I am privileged to be here back in my second home, Japan, and it gives me a great pleasure to speak to you today. Last year, I was awarded the Kavli Prize, and my research for it was made in Japan, based on the Made in Japan discovery. So 26 years ago, I was working for the NEC Basic Lab. I joined that institute back then, and at that time, the NEC Institute was known for providing researchers with the state-of-the-art environment. Therefore, under the stimulative environment, it had produced eventually 2 laureates of a Kavli Prize, Professor Ijima and myself. Now, from now on, allow me to switch to English and give my lecture.
I'd like to thank the organizers first for especially the Kavli Institute in Tokyo, and especially Ms. Enamoto, who made everything possible and organized this beautifully. So I'm going to talk about tiny holes. You understood this already. And the story starts, as I said, at NEC in 1989. And a colleague of mine gave me this article in this journal, Physics Today, in which I found this article by Arosh and Kleppner, 2 outstanding physicists, well, internationally known physicists, and in which they explain that if you put molecules or atoms in tiny holes or tiny structures, you can actually control their emission properties. This seemed absolutely fascinating to me, and so I wondered if I could make such a structure. And I turned to a colleague, which I shared office with, Dr. Ochiai, and asked him if he could make me such a structure. And he said, yes, this would be not very complicated. A small hole in a metal film, about 300 nanometers in diameter and 300 nanometers deep. Then he asked me how many, and I said I would like 100 million in a square centimeter. That was a very hard work, but he kindly made the effort to make this structure. Thanks to that, when I got it back, so you imagine a glass slide on which there's a gold film and a square centimeter of holes, I could actually see through with my own eyes through the holes. And I was surprised because I could see through like tinted glasses. And it surprised me because I knew that light could not normally go through such small holes. It's like people going through a keyhole in a door. That seemed not very possible. And so I tried to understand why, and I took a spectrum, a transmission spectrum. So here you imagine the glass, the film, and little holes, and I measured the light going through, and I see these very large peaks of light. And there was more light going through the holes than actually falling on the holes, which meant that something unusual was happening. And this was more than 100 to 1,000 times what well-known theory predicted by a physicist called Hans Bethe. And even worse, there was more holes going through the holes than actually fell on the holes, and this made it even more surprising. So I then tried to find a reason. It took many years before I found the reason, as Professor Murayama explained, nearly 9 years, because it was not until I met Peter Wolf at NEC in Princeton in laboratories in the United States that he told me that it was due to surface plasmons, or probably due to surface plasmons. So what is surface plasmons? Surface plasmons is another name for light that's trapped on the surface of a metal. And so essentially light got trapped on the metal surface, and this was what enabled this phenomena. So the reason for this, why most people didn't believe me when I first found this result, was because light, the transmission of light through tiny holes had been studied for many, many years. It was not something recent. The first study of small holes date back maybe 2,000 years. This was known that you could, if you took a small hole in a room, in a dark room, you get an image, opposite image, upside down image inside the room. This is known as a camera obscura, a dark chamber, and this is where we get the name for camera. Comes from this, photographic camera, modern camera. And this was used by painters, as you can see here, like Vermeer, famous Dutch painter. It's believed that he used those to make his beautiful paintings. In the first scientific study of light transmission through small holes was done by Grimaldi 350 years ago, an Italian scientist from Bologna. And he showed that light diffracts, makes a larger spot than you would expect from just the size of the holes. And from then on, this light was studied scientifically for many years through such systems. I would like to show this work by a very famous Indian scientist called Jagadish Bose. He was a botanist, a professor of botany in Calcutta. And he did a very important work on using not just holes in metals, but developing radio equipment. And he should have shared the Nobel Prize with Marconi at that time. He also had one very famous student, another Bose, from which we get the name, who worked with Einstein, and for which we get the word boson, which is a name, another particles of which light is a boson, like Higgs boson. We heard a lot about Higgs boson recently. That's where it comes from the student of Bose. So in this system, in this extraordinary transmission, as it's become known, light actually comes from the bottom here, hits the surface. This is the holes. and literally get stuck on the surface, and on the surface of the metal. And then it tunnels through to the other side, gets stuck on the second surface, and moves out. If maybe the young people here have seen the film Matrix, it's a bit like going through a wall in 3 steps. It's sort of a science fiction. It looks like science fiction. And every time, and all the light on the surface piles up on top of the holes and give rise to these peaks here. And this is what is the origin of this phenomena. And because the whole surface acts like an antenna, you can get more light through the holes than actually falling on the holes. Now you can change this. Here you have an example. It's a real image of some of these holes. And you can control the light, the color of the light going through the hole by just changing the distance between the holes. Very simple way. As you can see, these are real colors taken under an optical microscope. You can also change other factors to change the properties. Now, many, many structures have been studied since this over the last nearly 15, 16 years. And I'm going to give you some examples of structures like these and that, which are particularly interesting from a technological point of view. So this structure is known as a bullseye. It's probably the most famous aperture. Aperture as a whole, most famous aperture structure that are in this theme, on this area. So here you have a single hole surrounded by grooves, and this whole structure acts like an antenna. And all the light, this is a real image of light on the surface that piles up. It looks a bit like Fujisan. It has a little hole in the middle here. And this is how, here you can literally see how light piles up above the hole. Now, if you make similar grooves on the opposite side, like shown here, then the light is beamed outwards. And this you get a sub-wavelength source, very small light source, which is beaming the light like a flashlight or something like a lamp. And this is technologically very useful. It's been put on lasers and to improve the output of lasers. Single holes also have interesting properties. Single holes, the light that's transmitted by single holes, or the color of light that's transmitted by single holes, vary with the size and the shape of the hole. This was not understood before. People thought that single holes were just a little passage for light. And when you then look at the diffraction, you come back to this old story about diffraction of light. We realize that the diffraction of light, something that's in the physics textbooks, and that was thought to be well understood from the work in the 19th century and the 20th century, is not correct. When light goes through such real holes, there are 4 diffraction regimes, 4 ways the light diffracts, depending on the relative size of the light and the hole. And this, of course, will change the textbooks, physics textbooks of the university students in the future. So the implications of this subject of the EOT, or extraordinary optical transmission, there are many, many applications, and I will just show a few. The first application I'll show you about is biosensing for medical purposes. And this is already the subject of many reviews for science. And here's an example that comes from the United States. And of course, if you're not a scientist, this won't mean very much, but here, this whole phenomena is scaled to the infrared region where molecules vibrate. And you can see the signature of molecular vibrations. And this was done by Jim Coe in Ohio and his group. And here you can see very strong signal from a single nanometer layer of molecules. This normally requires 1 centimeter. Here we can see the same signal in 1 nanometer. So much orders of magnitude smaller. And this, of course, allows for the miniaturization of biomedical equipment. And this is what this is very useful for. Another example is by a group in Canada where they trap single molecules, proteins or enzymes inside a hole. And they can actually, there's so much light intensity just in the hole that it actually gets trapped. And then you can follow, in this structure, you can follow the behavior of the protein, how it changes shape, how it moves, the mechanics. Molecules have mechanics, and this you can actually follow at one protein at a time. Today, that's done with, very large amount, macroscopic amounts. So this is a very promising application. Another area of application is for devices, optoelectronics. And there I would like to show one of the most beautiful ones, which is done by Professor Ohashi and his colleagues at NEC, who's here today. And this was to try to make very fast computers. So when you use a PlayStation, which I don't use, but some young people might use some PlayStation, you need to have many CPUs synchronized so that the system is fast enough. So CPU is the brain of a computer or your portable phone. Normally you have one, here you have several. And they need to be synchronized to do this work together and to produce a very natural and fast response of the computer. To do this, one uses pulsed light. But to synchronize several CPUs, you need to have a very fast photodetector on the silicon. It turns out the silicon is not the ideal photodetector. And so they made a very small silicon photodetector on the chip and then added the antenna to collect a lot of light. And this way they made the world's fastest silicon photodetector. And this actually works has been tested by synchronizing many CPUs. Another a very simple example is filters on the camera. This comes from Caltech in California by Atwater's group. And here you have images of different Hall arrays, as you can see, to select color selectively, to use holes as filters for different colors. And you might wonder why you need this. Well, modern cameras are organized this way. Every color is collected at a different place inside the camera in this mosaic, known as Bayer mosaic. This means that when you take a photograph, you cannot just use that information right away. Inside your camera, there's a software that recalculates the image. That's why the very first electronic cameras gave sometimes very funny colors, because it had to decide what color, try to understand which color was observed outside. Here's an example. This is Fred Kavli. If you blow up the image, you take an image of him from very far away, you can see that it's going to be very difficult to determine the color of his skin, because a quarter of his face will be one pixel, one detector. And this, of course, it becomes even more critical if you put cameras in satellite imaging, which is used worldwide. So we tried to find a different way. Couldn't we just collect all the light at one point and sort it out? Was there a way to use our structures to improve this? So let's say in light falling here, green would go there, red would go there, blue would go there, to a different photodetector. This seemed like unlikely that this would work, but actually it does work. You put in here 3 gratings, and this is maybe for people with a science background. You put 3 gratings that actually are sensitive to different colors at the same place, and it still works, surprisingly. And then you get this kind of image. You see different colors at different openings. These are a real image, and when you change the orientation of light, the polarization of light, you actually see different bars light up. As you can see, different colors, they change color here as it turns. And this, of course, is very useful. This is 10% efficient. A modern camera is 25% efficient. So this is remarkably good when you consider that I'm not an engineer, and my team is not an engineering team. This is not optimized. So this photon sorting is useful. Now, what's the future of this subject? This is this area is called surface plasmon optics or plasmonics. And this is a title from a journal that says Plasmonics, the next big thing in nanotechnology. And here you see some holes and fire coming out. Now that, of course, is not a very positive image. This was not a very correct image. Hopefully it's not burning. And, but this area still has about 3,000 publications per year on this subject. That's a lot. A lot of scientists work in this field. And there are two areas of interest. One is for optoelectronics, telecommunication. The other is for medicine and sensors. And why would they want this for telecommunication? Well, the reason is that when you probably all have felt how hot your computer becomes, that's because it wastes a lot of energy. Internet is a huge, downloading on the internet is a very energetically consuming process. It's so consuming that it takes, roughly it's estimated, it uses 10% of the world's electricity right now. There's nothing green about the web. And the worst is downloading. And so the reason it's not the light going through the fibers, that's very fast and very efficient. But what's very inefficient is the processing by servers and transferring the information from one place to another. So this is an area where this kind of subject can probably find a solution or help find a solution to replace electronics by optics and make it very small. So what do I do? So I'm like Professor Kahn or Dr. Kahn said, I'm a person who likes to look for new things and always motivated by curiosity. And what fascinates me is something that I've, again, found related to holes, but which is the hybridization of light and matter. It's like mixing light and matter to change matter. And this, I discovered, I didn't realize this was possible, but it is. And this uses the vacuum field. So what is the vacuum field? So here's a little bit of a link between a modest effort at linking Alan Guth's talk and my little holes. So here's the universe, and here's my little holes. And why do I mention this? It's because I was taught when I was young that vacuum or space-time was nothing. And actually, it's not nothing. If you look at the speed of light, you see that the speed of light is, if the vacuum or the space-time was nothing, the speed of light would be infinite. It's not infinite. It's nearly the same as in glass, about 50% difference. So vacuum is more, nothingness is more like a dielectric. This is, again, a scientific term. It's more like glass than nothing. And most scientists don't think of it this way. And this comes out of sort of something called quantum electrodynamics. Now, vacuum has infinite number of states where light can go into. When light comes out of a lamp or out of this projector, it goes into these states. And all of these states have some minimal energy. And this minimal energy or fluctuation, actually, you can play with. And that's what I play with. So I do something that, I'm going to have to blow this up, hopefully. And I'm going to talk about something called strong coupling, where I mix light and matter, or light and vacuum. Can you put on the sound? Can somebody put on the sound of this computer? So here are metronomes. Initially, they are random. And little by little, they all start moving together. They're coupling oscillators. They couple through the beer cans here. So So I'll stop this now, quickly. And this is called strong coupling. This was discovered by Huygens, a Dutch physicist from the 17th century. He had big pendula clocks in his house, and he noticed that they got synchronized. And this, you can see this on YouTube, you can see it elsewhere, they're actually quite beautiful examples. And you can do the same thing between a material resonance and an optical resonance. And you get these new hybrid light matter states. And these hybrid light matter states have been studied for a long time in physics, but nobody has really looked at what it does to matter. And this is what interests me. And here this involves, this interaction involves virtual photons and inverts a vacuum field. So this occurs even in the dark. All you have to do is put matter inside some optical resonator that has the same color as the matter. So here is, for example, two mirrors where light is bouncing back and forth. Here are some molecules. You mix the two, and if the absorption of this molecule resonates with this cavity, optical resonance, you get a new material with new properties, new color. And many molecules are playing together here, just like there were many metronomes. Here there are many molecules playing with one optical resonance. And the strange thing is that as you increase the number of molecules inside here, these two states, these two new hybrid light matter states change energy and change color. This is as if when you come into the room, everybody gets taller. And as people leave the room, everybody becomes smaller. Okay? This is very bizarre to me, very unusual. And these states, these are collective states. So suddenly you have 100,000 molecules all working together. They're all oscillating together. 100,000. Now, if you're a chemist like me, that opens a world of possibilities. And I'll show you one example. So when I was at NEC, so I come back to NEC always because it marked my life. When I was at NEC, I learned that organic semiconductor was promising for the future. But the big problem was that in an organic semiconductor, electron hop from one molecule, this is a molecule, this is a molecule, electron hop from one molecule to another, and this is a very slow process. And so for the moment, organic semiconductors have not replaced silicon, because silicon can, in a silicon, the electrons flow like a river, like water in a river. And so I thought, well, if I now have if I connect 100,000 molecules, I should be able to change maybe the conductivity. And indeed, so I will show this just for the scientist, and I use Hall arrays again. I change the color, so I can tune the resonance of the color of the holes to that of the organic semiconductor. And when they're in tune, something happens. And this is again shown here. So I measure conductivity between two metal. Here we have the molecules. Here you have the Hall arrays. And something happens. And I'm just going to, this is again for physicists, but what you see is that every time that the molecules and the surface plasmons, the plasmons interact in the dark, the conductivity shoots up here and here and here. And this has never been seen before. It again was very hard to publish. It took a year, and we needed theory to publish this. And we were able to show that we can increase the conductivity of organic semiconductors by a factor of 10. Now this is a proof of principle. It opens a whole new door of possibilities, and we hope to further improve this so that organic semiconductors become real. Now, I hope I've shown you that you go through a journey starting with some basic finding, some funny thing. Discovery cannot be planned. A lot of government agencies want to plan research and plan discovery. That is not possible. Discovery is by definition accidental. Otherwise, it's not a discovery. And so the only thing you can do is change the organization. If you want to increase the chance of some new discoveries and new technology, you have to create the right environment. That's the key thing. Okay? That's what governments should worry about, agencies should worry about. And so with this, I would like to thank some of the key people who took me on this journey, who helped me along this journey. There are very many people involved. These are people at NEC, there are people here. It wasn't just the people who interacted scientifically with me. There's also the people who managed the environment, who created the environment that made NEC such a special place. And there are people here who made this possible. Of course, there are collaborators and students who worked on this subject. And finally, this is my group today in Strasbourg. Thank you for your attention.
Epson 博士、ありがとうございました。
Professor Epson, thank you very much. Since this is a precious opportunity, we would like to ask Professor Epson to answer questions. Please raise your hand if you have a question, and please wait until staff brings you the microphone. Are there any questions? There must be a question. Then, if I may, for 9 years, no one believed you, and how did you feel?
You have to believe in what you find. But I was encouraged by some people, like Dr. Kishida, who's here, Dr. Igarashi, who's here, and they told me not to give up. They said, you don't give up until you know the reason, because they thought it was important. And so I'm very grateful for them to encouraging me. I wasn't alone. You know? But I did other things in between. And I just didn't work on this. So I mentioned carbon nanotubes before. I actually did not discover carbon nanotubes. This was done by Ijima-san, but I discovered how to mass produce them. And so I made some of the experiments possible. So I worked on carbon nanotubes all the while doing this at the same time. So this kept me busy.
なるほど。くじけた時には違うことをやってみるのもいいってことですね。
So if you let down, then you must try at other things in parallel, right? All right. Any other question? Please keep raising your hand. The microphone will be brought up to you. Well, at the very outset, you said that 100 million holes will be milled in the 1 square centimeter. So why did you think of this number of holes?
Because I'm a chemist, and a chemist at that time. Things have changed today. Today we can look at very small objects, nanometer-size objects. But 25 years ago, it was not possible to look at such. It was not easy to look at such small objects. So I wanted something I could measure with a machine of the time, which needed about a square centimeter. All the measurements were done on typically on 1 square centimeter. That's all. No specific reason, except to be able to look at, to be able to make measurement. So this was lucky.
他にはどうですか?
All right. Anything else? Yes, please. This side of the hall. Microphone, please. About the light, you said that the transmissivity of light was discovered. So you were working on carbon nanotube during the daytime and maybe working on the light during the nighttime. So what kind of lifestyle were you leading at that time? You are working throughout the day, right? 24/7. I was really busy. Yeah, quite busy, for sure. So at that time, the only thing I done was research.
I didn't have anything else to worry about because NEC gave me the funding. I didn't have to teach. I had the funding. I had the environment. I had colleagues like you. And so I didn't need to worry about other things. So I only had to worry about research. And so there was enough time in one day to do both things.
羨ましい話ですね。
I envy you for that very much. Anything else? Yes. The person on that extreme side, please. You said that a small hole was milled in the silver film. Did you handle other kind of metals as well, so that any metal sheet will do?
Yes. So this also works. Actually, it works in other, not just with light. It also works with sound. So you can put a screen. The people have done experiments where they put a screen for sound. And with no holes, sound comes through. With holes, some sounds don't come through. It's very strange. I put a screen, so with this system you can also block sound or block light. So you can stop sound from going through a screen by making holes in the screen, which is not intuitive. You would think the reverse. You would think if you make holes, a lot of sound came through. But actually the reverse happens. So one application is in factories for sound where a lot of constant noise, and you want to see in, so you make lots of holes, and you stop the sound, but you can see through. Like a microwave oven screen. A microwave oven has a screen with little holes. You can see through with your eyes, but microwave doesn't come through.
不思議ですね。
That's quite interesting. Very the source of wonder, right? Let's go to another question. Well, you said that the discovery is an accident, right? It's not planned. So by definition, you said that the discovery is an accident, and I totally agree with you.
And the agency needs to take care of the accident, right? Do you have any good idea how they can take care of accident to increase the number of accidents?
Give scientists more time to concentrate on research, less bureaucracy.
Less bureaucracy.
Less
so who take care of the bureaucracy?
Yeah, I think if you organize small teams, less bureaucracy, you will get better output. Okay. No? That's a key thing.
ありがとうございました。
Thank you. Yeah, that's a good story. I hope people from MEXT is within this room, right?
他に質問があれば。はい、一番。
Anything else? The person at the very back. I was not able to understand your lecture fully, but you talked about a hole on which the light piles up. Does it mean that the light is stopping there so that the speed of light becomes slow?
No. It spreads. It comes down and scatters. I don't know the Japanese word for that, but it spreads on the surface. It goes poof. It's like water hitting a surface and spreading. And so the light comes and spreads on the surface and gets trapped.
But then it can come back out.
And then it can come out, then it can leave again for the same process. That's the magic of physics.
はい、まだ質問ありますでしょうか。
Any other question? One more question from you? All right, you can ask your follow-up question. Then let's go to the other side, the person. I saw some hands there. Toward the front, fourth row or third row from front.
The smallest size of hole light can pass? It's an atomic level hole. Is it possible to pass?
No, eventually, as the hole gets smaller compared to the wavelength, of course it falls down. The light falls down. I think the smallest we have studied is maybe 50 nanometers.
50.
So 10 times smaller than wavelength, maybe. You still get light through, much more than traditional theory predicts, but still not very little. So it's not so interesting. There's an optimal size.
Okay, thank you.
あと一つか二つぐらい質問を取れると。
We can entertain one or two more questions. Yes, please. maybe I heard you wrong, but you talked about organic semiconductor. In order to build the silicon, you said that the connectivity can be used. So in that case, the light will go through a very small hole, and that can be a source of a combination and collaboration.
But I don't use any light here. Here I don't use any light. This is done in the dark. It's the antenna here catches the vacuum energy, vacuum fluctuations. Okay? So it's the vacuum fluctuations, which is a very strange thing. Probably Alan Guth is one of the few people who understand what this is. I hardly understand it, but I like playing with it. It sounds... When I submit papers like this, the comments from referees is this is science fiction. This takes a long time to publish, not 9 years, but nearly. Okay, so this is just in the dark, and it's just because it resonates with the material. The holes are not so important. It's just easier to do the experiment. Okay?
Thank you very much.
Yeah.
はい、じゃあそこの方。
Yes, that person over there. Well, you talked about light going through the hole milled in the metal surface. Is that a transmission of grating on the level of the photon? Does it happen on the electromagnetic level as well? So photon go through it?
That's always in physics. Photon and the wave nature and the photon nature of light is two sides of the same thing. It's two sides of the same thing. It's like, I often give an example. This looks like a circle. This is your photon. This looks like a rectangle. It's still the same photon. There's two different images. So the wave aspect, I don't know if you're a scientist or not, but the wave aspect is the probability of where the light will go. Energy is sort of the photon aspect. Okay? So for us, this is not, we use the wave aspect to tell where the light will go. But the energy is in the photon part, the photon type aspect. But it's one thing, not two things.
よろしいでしょうか。じゃあ、少し。
All right, so we're a little bit early, but maybe we could conclude the Q&A session. Please give a warm round of applause to the speaker, Dr. Epson.
ありがとうございました。